Bonjour, good afternoon. Okay, so I want to get my presentation started. So my topic is really about the sustainability, what we do in TORAY performance material. It's sustainable thermoplastic composites, TORAY PMCs effort for zero discharge future. Just a little bit of background of myself. I'm Jinfen Zhuge, the R&D director of TORAY Performance Material Corporation. I had a PhD degree in mechanical engineering from University of Central Florida and MBA degree from Jackson University. I joined the PMC since 2019, and I worked on lots of projects, but mainly focused on sustainability and recycling. Before that, I was a research scientist in SABIC. My specialty is formulation design, compounding, dealing with things like flame retardants, fillers, and lubricants. TORAY Performance Material, who are we? We have been in the thermoplastic industry, thermoplastic composite industry for more than 30 years. To date, we have shipped over 200 million thermoplastic parts to our customer, and our process is very fast, rapid speed. We're doing most of our parts by vacuum forming, thermal forming, and those are good. The thermoplastic composite have a good combination of lightweight and high strength. Our material can be found applications in athletic footwears, sports and recreation, podiatry, orthopedics, consumer electronics, automotive, and industrial. So why thermoplastic? As I said earlier, one of the biggest things for thermoplastic composite is it's fast forming time, 30 seconds only sometimes. So even today, every year we're shipping a couple million parts to our customer because of that benefit. Another big advantage for a thermoplastic composite is that we'll be able to utilize or capitalize the development work from the thermoplastic industry that opens the door for basically unlimited choice of thermoplastic resin, PA6, PCA, PBT, you name it, and different type of effect, right? Last but not least, the thermoplastic resin, thermoplastic composite, as you know, you can form it, you can melt it again, compound it again, over and over to recycle them. It's much easier compared to thermoset material. So my focus today is really about our approach to do the recycling. I think we probably one of the handful companies in this world that not only we produce thermoplastic composite material in large volume, but also we take care of our own scrap. Not we are buying recycled raw material source from outside, but we take care of our own scrap material. So of course, different approaches. You can do it by burn them off, right? In calcination, that produce lots of waste, pollute the environment. Of course, more and more regulation comes up that prevent you from doing that. The second approach is, I guess, most commonly used right now is sent to landfill. It's relatively cheap, but the social and the environmental cost is very high. Actually, there was a study published in 2018 in the United States. About more than 80% of the plastic material, plastic waste, was sent to landfill. Only another 13%, about 13% is burned to recover the energy out of it. And then only about 5% was truly recycled. Another approach we can do is to recover the fiber, because sometimes the carbon fiber is very valuable, and with the price increase, it may make sense to recover the carbon fiber. However, the process probably involves two ways, right? One is Porous is the material, you burn off the resin, you get a carbon fiber. That creates a problem itself. You have a waste to deal with. Or you can chemically take out, melt the matrix and take out the fiber. That's another very difficult process you involve with the chemical waste. And most importantly, this approach doesn't take the full advantage of the thermoplastic material. As I said, thermoplastic can melt it and over again. So I think to us, the most economic way, the most environment-friendly way is to chop them down into smaller particles, and then we put some new additive to it, formulate it, make a new life out of that waste material. So that's the focus of my presentation today. So this is a brief introduction of how our process is, right? Where the scrap material is generated. So we started with process of making a thermoplastic composite panel. Typically, it's a flat panel, and then we cut the parts out of this panel. So as you see, we generate quite a bit of skeleton because you cut the parts out, you have skeleton left over. So that is one source of our scrap. The second source is you have the parts, then you form those parts, and we got rejected parts. Means some scrap material come out from this source as well. Then we ship it to customer. So we have two streams of waste material come out from our process. So what we do is we take this material, we break them down into much smaller pieces. In that way, we can add new additives, chemicals into it to making reformulate the waste material, to making either resin out of it or injection moldable pellet out of it. So now I want to talk about first one, how do we do the recycle with injection molding. So we take the material and we create the first table is really to understand the design space of our scrap material. So our material is mostly PMMA-based polymer matrix, and with carbon fiber, glass fiber as a hybrid reinforcement. So we take that material, we want to blend with some virgin PMMA, and the first approach to understand the design space, we have our material from the scrap material content from 7%, 7.5%, to as high as 67%, and to see how they mix, how they compound. And then the next approach is, as we have a better understanding of the processability of this recycled material, some of our customers, they want to have the material is relatively flexible, has more ductility to it. As some of you may be familiar with polymer, the PMMA is relatively brittle. So we add different type of TPU, different flow, high flow, low flow TPU into a system to see how that works. So this is a trial we did last year. So to understand, first to understand the design space, as you see, when I had 67% of the recycled content in the formulation, it is very difficult to extrude. Then we reduce the scrap amount to 20% in terms of weight. And as you see, the extrusion process is much more smooth. So with trial and error, with some experience, we find out anything above 50% is sort of difficult to compounding. So we try to keep it down below 50%. So this is a material property we got out from that DOE. As you see from the first table, this row is fiber content, and we have tensile property, flexure property, tensile elongation. So the baseline is just a PMMA resin. It has very good, relatively good tensile elongation. But as you increase the fiber content, the tensile elongation drops dramatically. But at the same time, mechanical property improves. Tensile strength, tensile modulus improves. Second table is where we introduce the TPU into the system. So compared to the first table, you see the mechanical strength kind of sacrificed because of TPU you add to the system. But you see the tensile elongation increase a lot. All the way we can achieve about 7.8% tensile elongation with TPU and PMMA combination. We did another analysis of how the uniformity of our final parts look like. Because one of the biggest challenges for recycled material is that you don't have a good uniformity. The beauty of our recycled material is that this is a so-called post-industrial waste stream. It has not gone through consumer cycle yet. So the material is, in a way, is relatively virgin, very nice, beautiful, homogeneous material. So we did the analysis of the fiber distribution. The first sample you can see we put in an oven set at 600 degrees C for 30 minutes. There's a carbon in there and some leftover charge. And then we keep burning it to 600 degrees C for 2 hours. All this carbon are all being decomposed, oxidized, left over with clean glass fiber. That's how we use to determine the distribution of the fiber. So we take the end sections and middle section, we did the weight analysis. So based on theory, there should be about 18% of glass fiber throughout the sample. And the calculation-based actual weight is very close to 18%, which means it's very uniform. The second study, which we hope we can do, but we don't have the capability to do it, is to really understand the fiber length distribution of the material. I can only cite a citation here. It's a literature research by a group. They take this is a compounding extruder. Here's how the material is fed to, and they take a sample out from S1, S2, all the way to S7. So as the material goes through the compounding process, here's the fiber distribution. So from S1, you can see the fiber distribution is all everywhere. You have 0.5, you have 3.5 millimeter. But as you go more and more compounding, go through the compounding process, it's more homogeneous. So mostly the fiber distribution is around the 0.5 millimeter. So that also kind of tell us, visually we can also see it, that the fiber length distribution is also very good. So we have a good distribution on the fiber weight and also fiber length. So we take the material out, and here is an example of the pallet. If you are interested to talk with us more, please come to visit us in the Hall 6 TORAY booth. We have samples there. You can take a look. So we did this. For some of you guys know about the thermoplastic compounding, there's a technique called the spiral flow testing. So basically, you take the pellet, melt them, injection mold into a spiral flow. And of course, the longer it's shooting out, the better the flow is. So here's the correlation. As you see, with 40% of fiber content, we can only achieve 10 inch. And 20% we got to 30 inch. And with the help of TPU and reduce further the fiber content, we'll be able to achieve 35 inch today. And of course, we can easily, with 35 inch, the flow is relatively good, manageable. Then we can make a complex shape out of this material. We do injection molding. You have the texture to the surface, different curvature to the parts as well. So, by the way, those are only 1 millimeter thick samples. Another thing we can do for the material, recycled material, is carbon fiber is good for its strength, but also conductivity of the carbon fiber is also another interesting feature for it. So we take our material, we did some electrical surface conductivity test. The samples we have are from anywhere 10 to the 7th to 10 to the 12th, or some of them with higher carbon fiber content can achieve below 10 to the 7th, the resistivity. And we also look at some of the market available solutions specifically for electrical conductivity. Those are between 10 to the 2th, 10 to the 2nd, 10 to the 5th, 10 to the 10th. So we are well within that range of application. And as you see, there's a spectrum of surface conductivity. When conductivity is below 10 to the 6th, we call it conductive material. When the conductivity is between 10 to the 6th to 10 to the 12th, we call it static dissipative material. And then if the resistivity is even higher, become insulative material. So we are in a static dissipative material range. Then we also compare the mechanical properties with those market available solutions. The black line spread chart is our recycled material. As you can see, the material has about very good combination of the tensile strength, tensile modulus, flex and flex strength, flex modulus. However, this is a PMMA material, so the impact is relatively low compared to other market available solution. However, many times those kind of material is only used as a functional surface. The structural property or mechanical property matters, but doesn't matter that much. So we can find application for enclosures that we want shield from external interference. We can also find application for static dissipation, especially if this application is very important for the gas station, where the spark can create an explosion, or possibly can use for EMI shielding as well. So this is another recycle approach we are recently working on, early stage. We try to create a liquid resin out of that recycled material. And we blend with our proprietary formulation. And you see with the recycled material, we can pretty much making a resin similar like syrup or honey. So we can use this resin to making prepreg out of this material. And again, it's a PMMA based. So it's a thermoplastic. After it's cured, we can still thermoform it. Then we compare our resin with some of the market available liquid thermoplastic solution. As you can see, the properties are very much comparable. And because those resin already have those little bit of fiber from the previous life, they have some slightly better mechanical properties as well. And we can cure the resin based on application from 2 minutes all the way to 2 hours. And the viscosity we can achieve is 170 points to 30,000 centipoints. And then we did the experiments. We take a glass fiber, a woven glass fabric. We laminated it with this resin. We make a panel out of it. And it's 1 millimeter thick with 40% glass fiber reinforcement. And we compare with some of the virgin resins we have available. And you can see the properties are very much comparable. We can pretty much say the recycled material achieves about 90–95% of the virgin material property. So where are the application of this recycled material? That's what we were thinking. So maybe it can be an opportunity for wind industry. There was a study saying that from 2012, there are about 5% of the overall energy is generated by wind. And by 2040, it will become 14%. It's quite a bit of increase. Of course, not as impressive as the solar energy, but still it's a big, sizable increase. With that comes a problem. Most of the wind turbine industry, they're using thermoset material, right? And thermoset glass fiber. So what about the end of life? What do we do is the end of life of the wind turbine? Those are huge. So the study told us that with all this energy increase, production increase, we will be generating about 2 million metric tons of the waste material because of the decommissioning of the wind turbine by 2050. 2 million metric tons. Think about that, right? How can we deal with those thermoset glass fiber material? Those have 80 to 90% composite material, those wind turbine blade. 60 to 70% is fiber, mostly glass fiber, and then you have less resin. Here's a picture of the wind turbine in the landfill, right? It's huge. So can we use the thermoplastic resin to making wind turbine with that, the ones we created, that it's work as if a thermoset. You can pre-preg it, you can cure it, but in the end of life, we did all the compounding, we did all the recycling work already done. It's doable, right? So with that, I conclude my presentation. Thank you for your attention. Any questions?
Can you stand up, please? And like this.
Hello, thank you for this presentation. What is the commercial name of your liquid resin PMMA? What is the name of your resin PMMA, commercial name?
Oh, we don't have a name yet. It's still in the early experimental stage.
Okay.
Yes. Yes. Thank you very much.